My name is Cooper Stone, and this is my Physics 2212 Lab 4 about circuits. So the purpose of this lab is to use circuit elements such as an ammeter, voltmeter, light bulb, and resistor to test things such as the time constant, potential differences, and current across a circuit. And here we're assuming accuracy of measuring instruments. We're disregarding the internal resistance of wires because we're doing this lab in real life instead of using the simulation as in the directions. And our major finding was that the time constant was equal to 6.079 seconds. So here's some essential concepts, the first one being the node rule, which states that current flowing into a node equals the current flowing out of a node. And the loop rule, which states that the potential difference across a closed loop of current is equal to 0. And both of these stem from the charge conservation and energy conservation laws. Some other central concepts include resistance, which especially include Ohm's law, which states that voltage is equal to current times resistance. And then that for resistors in series, the total resistance is equal to the sum of the individual resistances, whereas for resistors in parallel, the inverse of the total resistance is equal to the sum of the inverses of the individual resistances. Capacitors work in an opposite way almost. Resistors resist the flow of current, whereas capacitors store charge between two separated metal plates. And in this case, as you can see, that's the formula for field of a constant and a potential difference across a capacitor. For capacitors in series, the inverse of the net capacitance is equal to the sum of the inverses of all the capacitances, whereas when they're in parallel, the capacitance is equal to the sum of all the individual capacitances. So this lab was entirely experimental, using things such as resistors, ammeters, voltmeters, things like that. And we determined things such as potential differences across different parts of the circuit and the time constant by measuring times for a capacitor to discharge and for a light bulb to go out across a circuit. So here are some basic diagrams of the system. The top one shows the original simple circuit, which just involves measuring voltage across different parts and current. And then the blue lines in the figure below it shows between the points at which potential was measured. So for example, the potential difference was measured between points A and B, B and C, C and D, so on. And then at the bottom you can see the model of the circuit used to determine the time constant near the end. So this part we examine charge and energy conservation. So here we determine the current at two different spots, and because of conservation of current, it's consistent throughout the entire circuit, and it was read to be approximately 0.02 amps, and it was calculated to be about 0.0204 amps. And the only reason the instrument wasn't more precise is because it only went to the hundredths place, so these results matched. Additionally, as seen in this figure, the potential differences across areas such as B and C, D and E, and things where there are no resistors or any other elements in between, the change of potential is 0 at those spots. And because the batteries contribute a total potential difference of 3 volts, the portions where there is a potential difference, they sum up to be 3 volts as well. So that way there is a net potential change of 0 volts. And here you can see that demonstrated where the batteries create that 3 volt potential difference. And then the other elements between C and D and E and F contribute to restoring a net 0 volt potential difference across the circuit. And then here's another part where, using those values for a potential, I found the resistance of the resistors. And although they gave it to me originally in ohms, like 47 and 100, I used the values I calculated to find the theoretical values of resistance, which were almost exactly correct. And for the final part, here's a picture showing how I measured how the charge changed over time to try and determine the time constant. And those are the discharging times for the two resistors. And then here, you can see how when I used the 30 ohm resistor, I measured potential difference over time. And then by plotting the natural log of potential difference over the original potential as a function of time, I found the slope to be negative 0.1645, which is equal to the negative inverse of time constant, allowing me to calculate the time constant, 6.079 seconds. So the experimental value is 6.079 seconds, whereas the theoretical value is 6 seconds, so that was very close and accurate. Sources of error include human error and inaccuracy of equipment. And what if I was doing this lab in real life and used an actual ammeter? I did use it in real life, and that contributed to resistance due to the internal resistance of the ammeter. And what if I was doing this lab in real life and used a real battery? Again, I did that, and in an ideal world, the capacitor charged instantly, but due to internal resistance of the wires, this was not the case.